Hello everyone. So my name is Camille Chattard. I am working at Specific Polymers, a French company specializing in designing innovative polymer materials. So today I will present our work we made in the frame of the BIO-UPTAKE project on debonding on demand adhesives. And I will show you how we can enable strong bonding during use, but easy separation when needed. So let's start with the concept of reversible adhesives. So the debonding on demand means that two substrates can be strongly bonding during their lifetime, but separated intentionally when required. So this is particularly important for recycling and reuse because the classical permanent adhesives are not able to of multi-component materials. So the challenge here is to have two opposite needs. First, a strong adhesion during the use, and secondly, a clean removal without damaging the substrates. And to achieve this, we can apply external triggers. So different triggers can be applied, such as chemical ones, electrical ones, or also mechanical. And in our case, we focused on thermal activation because it is a simple way to achieve separation, fast and also solvent-free. So the key mechanism behind our system is based on covalent adaptable networks, or CANs. So CANs are polymers with dynamic covalent bonds. That means that the network can reorganize under certain conditions. So there are two main types of CANs. The associative ones, where the bonds exchange upon activation, but the cross-link density remains intact all along the process. And the dissociative CANs, where bonds break upon activation, which enables the debonding. Our system uses the dissociative approach, which is ideal for a clean separation. And specifically, it relies on a Diels-Alder chemistry using furan and maleiimide groups. So in that case, under normal conditions, typically from ambient temperature up to 70 degrees, the components remain stable and strongly bonded. But when we hit above 80 degrees, the bonds start to break in a reversible way, and this allows the separation of the substrates. So now let's have a look at our actual adhesive formulation. So it's a two-component system based on a modified bio-based epoxy resin, which is combined with a reversible Diels-Alder network. And the key advantage of this solution is the ease of use, because it allows the use of standard application methods such as spray coating or bar coating. Also, curing is made at ambient to mild temperatures up to 60 degrees. And this solution is compatible with common substrates such as metal, plastic, or composites. So when debonding is needed, a simple heating using, for example, an oven or a heat gun triggers the process. And within minutes, we can observe almost complete loss of adhesion, which allows the clean separation with minimal residue. So this is illustrated on this graph, which displays the adhesion strengths on various substrates at ambient temperature. So we can see here that the adhesion strength is quite high, and after thermal activation, we have a complete loss of adhesion. To validate the concept, we also tested two prototypes to show the practical relevance of our approach, and this was made in collaboration with partners from the BIO-UPTAKE project. So first, a garbage can lid, which combines PLA organosheet and reinforced polyamide. And secondly, a bathroom ceiling panel combining composite and wood. And this prototype is illustrated on this video. So we begin by applying the adhesive onto one of the substrates, and the second component is then assembled to ensure proper contact between both surfaces. Then the system undergoes thermal curing, and at this stage, the components are strongly bonded and ready for use. And when separation is required, heat is applied, triggering the reversible chemistry. And the adhesive loses its strength, allowing easy disassembly of the substrate, as showed during this video. So, based on this proof of concept, we are now working on 3 key aspects. First, tuning the performance, especially by adjusting the debonding temperature through the chemical design of desader adducts. Secondly, the optimization of the processability, for example, by controlling the viscosity with additives or through raw material selection to expand the range of possible application methods. And third, the improvement of the sustainability by increasing the bio-based content of our formulation. And these developments aim to make the technology even more adaptable or eco-friendly. So thank you for your attention, and I will be happy to take your question at the end of the session. And now I think I leave the floor to Julio from Moses Products.
So thank you very much. Thank you all for assisting here. I'm going to talk about the injection molding and how we will first explain a little bit about the injection molding, and then in which way do we take Camille's additives materials and we implement them into our system in order to develop a complex system that can be separated in the different parts. So first of all, the injection molding, we take it from the lab to the industry. We need to understand the special needs, the objective, and the focus. I will go fast on this. But it's really important for us to combine the different material properties, because we are going to develop, in this case, we are going to focus in a container lid, and we need to understand the properties that we need in order to combine these materials. Thermoplastic materials, and also the adhesive that Camille and SP is providing to us, and how these materials are going to behave in the injection molding machine. We need also to understand the changes that we are going to need in terms of production of the components, how this product is going to change from one material to several materials, and what's that going to mean in terms of technologies that we need to transfer into our process. Okay, we have several possibilities in here. Of course, taking a robot to moving the material from one cavity to another cavity. We have also the possibility of rotating the mold so that we can inject several materials, or we have the core-back technology, in which what we do is to foam the material and produce internal bubbles, let's say, into the plastic that will allow us to reduce the final weight. In our case, the challenge is to bond between the different components that might not be mechanical, but we want it to be a chemical bond. There are several factors influencing this: temperature, pressure, of course, during the injection, because you have to understand that during the injection, the material that is going to be injected is going to be melted, so at really high temperatures, and is going to be at high pressures in order to fill the whole cavity in just 1 second, because that's the time that we usually use. We are talking about 200 bars suffered by the material. So the amount of pressure that can be transferred into the materials that we are over injecting is quite big. And we have also to take into account the shrinkage differences. What I mean with this is that we are going to have 2 materials at 2 different temperatures, and that might mean that before the epoxy resin is properly cured in the bond between both materials, we are going to suffer a lot of stress, and we are going to put this interlaminate or laminate material that will bond in a critical condition, okay? Because we will have one material shrinking at one point and the other on another, so we can suffer the lamination points. Importance of the simulation and the evaluation of the bond strength, I will go directly to the case. Okay, our objective specifically is to take this lid and make it enhance it for the end of life, circular economy, and be able to revalorize different streams, the different materials that we are going to use. Okay, we were working, I will be fast, working in several grades. So we finally decided to move on, evaluated them, and we finally decided to move on just with one reinforced with carbon fiber and another reinforced with wood fiber. But the main point for us is to understand the design. For this, what we did first of all was to pass the lead into the computer. Okay, and now, sorry, it's not loading. What we did is to redesign the material, the final product, so that it will be possible to take it into these several components part. Sorry, it's not loading to the next slide. Now, you can see here that what we did was this change. Okay, and what we decided was to put some nerves, and we are going to use the epoxy developed by Camille in the interface between the laminate and these nerves. The simulations verified that it was possible to do it with our injection point. This is the filling, and here is the main point: how to prepare these materials and how to put this bonding material into the laminate. We first started with by hand, painting the laminate by hand, and then we move on to a 3D printing machine. Okay, in this case, we are going to use it just with a brush. So we are just making a 2D simulation. This in the 3D printer, we have the overall geometry of the lid, and what we are doing is transferring just a few microns. Okay, we are talking about 100 microns, 200 microns maximum that we are putting in this case in the shape of that we want, in the final shape that we are going to over inject. It is really important, the position. Okay, and also for us it was critical that the material was, that the epoxy was as thin as possible and as thin also possible. Keep in mind that once it's finished and we have finally applied this solution, we are going to take this laminate in which we have painted, I will say, I apply the epoxy, okay, and we are going to put it into the mold. In there we have a problem if we transfer the epoxy to the mold, because then after one injection nothing will happen, but after several injections we will have epoxy all over and we will have problems in the lamination. So we took the laminate, we place it into the mold, we anchor it, and we properly position it so that it will fit with the other side of the injection molding. Okay, here it's I hope it's blocked again. Okay, yeah, and we over inject it. We have in here the different steps. Laminate is thermoformed to finally introduce, so that we have the shape. And once we have done the injection, we have to match perfectly the polyamide that we are over injecting with the cans that we just draw on the laminate. Finally, we obtain these materials. Okay, it was, and as you can see, and what I was meaning with the thin part is that in these points we need to assure that we have the epoxy. Regarding the temperatures of action from our side, it was quite easy, because in the case of the polyamide, we over injected with a mold at 90 degrees. So we first activated the epoxy and then we put it into the mold, and just the temperatures of the process themselves were keeping this epoxy activated and allow us to do the over injection. Once we finish the over injection, we take the part out and cool it down, so that we avoid any feasibility of to separate. Okay, we make the epoxy strong again, let's say, from our side, and with this we can use the part. This is the final part that we have done, and during these weeks, what we have been doing and demonstrating is that okay, the lead is working, and we have been able to process it and manufacture a product with these three components. And once we heat up the material, we can remove the overall nerves, and we can mill these nerves and use them again for another injection molding. So in this way, it was a critical point to demonstrate not only the importance of the interface and validate how we should apply the epoxy, but also that after applying it, it works as we expected, and we are able to separate the materials. So it was a fast explanation. I hope everything is clear, and if there is any question, I will be happy to answer.